Hello, AP Chem. It is now Unit 7 time. So this is about equilibrium or equilibrium. So now equilibrium is a state of a reaction such that you can almost say that the reaction is at a quote unquote standstill. Now, the reason why I put that in air quotes is because the reaction really isn't at a standstill. So basically what's actually happening is if we have A plus B turns into C, and then C can, of course, go back into C turns into A plus B, right? Now, let's give these reactions the rate constants K1 and K2. Now, what equilibrium is the rate of the first reaction is equal to the rate of the second reaction. Essentially, K1 equals K1A B is equal to K2C. And so, if you're looking at from a rate perspective, this is actually what's happening. Uh, Now, if you're looking at it from a more thermodynamic perspective, what's actually happening is that there is no more energy being released, right? So let's get so let's get on to some calculations. So now the core pillar of this unit is going to be able to calculate the rate constant K. Now there are two types of K, Kc and Kp. Kc, as you can probably tell, deals with concentrations in aqueous solution. Kp deals with pressures and gases. So concentrations and pressures, they're going to be applied in different ways. So, for example, right, uh, you have an aqueous solution system, like a dissolution or a reaction that's actually happening in aqueous solution that's going to use Kc. If you have a gaseous reaction, that's going to use Kp. Now, for Kc, you don't actually use every single part of the reaction, right? There are going to be some parts that are going to be left out. For both of these, actually. Namely, the parts that are going to be left out are solids. Okay? And solids and liquids. Those are the only things that are going to be left out. So if you have water in your equation as a liquid, that's not going to be in there. However, water as a gas, that's going to go into Kp. If you have, so let's give an example, shall we? So, if we have calcium carbonate, CaCO3, this spontaneously decomposes, well, not spontaneously, really. This decomposes into CaO plus CO2 as a gas. And now so now a core component of all reactions that you must write for this exam is you have to write the states. If you don't write the states, let's go ahead and say that you didn't write the states here, and give an example of what a wrong K equation will look like. Okay? So we'll say that this is a student who only knows that CO2 is a gas. K is equal to, no, this should be pressure. Now, the problem with this thing, right, is, well, yes, it looks correct, it's including solids, and that is why including states is so important, is you reduce your rate of error. Okay? So, let's include the states now. Solid, solid, right? And so now, using our rule about K's, is that no solids are included. So that means calcium carbonate is not going to be in our K equation, and calcium oxide is not going to be in our K equation, which means that carbon dioxide is the only thing that's going to be in our K equation. So, K, in this case, it's going to be Kp since it's gas, is going to be equal to, well, the pressure of carbon dioxide. Okay? Now, if we had a gaseous reactant decomposing into solids, then it will be 1 over that gas reactant. The reason why is actually how K is calculated. So K is calculated by, let's go ahead and erase this up here, right? So for the reaction A, aqueous, plus B, aqueous, turns into C, aqueous, and D, aqueous, the Kc equation is going to be equal to the products C, D, over the reactants A, B. And now, of course, you're saying, well, what happens if I have coefficients there? So the proper definition that's given in most textbooks is AA plus BB turns into CC plus DD. If these are in aqueous solutions, then the K equation, or Kc's equation, remember, all of them are in aqueous solutions, so they're all going to be counted in the K equation. So the K equation is going to be C to the C plus D to the D over A to the A times B to the B. What that's essentially saying is that you'd have your reactant or product, right? We'll say E for simplicity's sake. And you raise it to your coefficient. So, chemical raised to the coefficient. And now we know the fundamentals of K, which will help us get through everything else in this unit. So now, let's go on to 7.4 and 7.6, which I have grouped together since I believe them to be very similar. So, K and Q, they're calculated in very much the same ways. However, K is dealing with at equilibrium, Q is dealing with right now. So, K is at equilibrium. And Q, again, is at right now. So, we can actually do some comparisons of Q with K. So, Q and K. So, if for the reaction A plus B turns into C plus D, right? Our K equation is going to be equal to C D. Actually, I should probably do this the way the textbook defines it. So C to the C, D to the D, over A to the A, times B to the B. So Q, then, is going to be much like the same way. However, since these are all equilibrium, we're going to add like a little time t equals 0. And really, all you have to remember for Q is that you have to differentiate it with K, because K equations are incredibly dastardly like this, right? Because again, you want to minimize your rate of error, right? That's how you get the most points. So, what you really want to do is differentiate how you write Q and K, because that's how you're going to get the most points and minimize your rate of error. Okay? So, if Q is greater than K, meaning that C to the C times D to the D over A to the A and times B to the B at time t equals 0 is greater than that time where it's equilibrium, then that means that there's too much product. The reaction goes to the left, or towards the reactants. If Q is less than K, that means that the denominator is too big now. If Q was greater than K, that means that our numerator is too big. If Q is less than K, that means our denominator is too big. It's math, really, fraction math. So this means that it goes to the right, towards the products. And now, for the third and final case, Q is equal to K, that means that both the numerator and the denominator match the K equation, or expression, I should say, which means that it doesn't go anywhere. It's at equilibrium. So if we give an example right here, right? Q, sorry. Let's give an example of the reaction to produce hydrogen iodide. This has a lot of industrial purposes. It's used to make hydroiodic acid, which is very strong acid. So you could see why the regulation of this equilibrium is so incredibly important. So now, let's calculate Q. Sorry, I got ahead of myself. If K equals 50, H2, again, at time t equals 0, is equal to 10, or 0.10 molar. I2, again, at time t equals 0, is equal to 0.10 molar. And HI is equal to 0.50 molar. Is the system at equilibrium, and which way does the system shift if it isn't? Okay, so Q here, right? Let's calculate Q. So what we have here is HI over H2 I2. Okay. Now I know that this says gas, right? But for certain purposes, you can actually treat gas as if it were a concentration. Most notably, if it's in a 1 liter, if it's in a 1 liter container, because that's literally moles over liters. Okay. Now remember, A to the A, C to the C times D to the D over A to the A times B to the B. So we raise our concentrations here by our coefficients, which means that HI here needs to be raised to the 2. So we have 0.5 times 0.5 divided by 0.1 divided by 0.1 yet again. So we have that Q equals 25, which means that Q is less than K, which means that the system is not at equilibrium. So this means that the system, if we go to our little chart here, Q is less than K, so it's a middle case, it goes to the right towards the products, which means that more HI will be created. So, let's see, we can actually calculate a sort of like how much it will go by, right? So, if we use that same equation, H2 plus I2 turns into 2HI, we can actually do something called an ICE table, ICE. Initial change equilibrium. So, let's do it again. H2 initial concentration is 0.10, I2 is initial concentration is 0.10, and HI initial concentration is 0.50. Now we already established that Q is less than K, which means that the reaction will shift towards that way. So what we can actually do here, if we want to calculate the final concentration, is say H2, if we say that H2 decreased by a certain amount x, right? That means that at equilibrium, the concentration of H2 will be 0.10 minus x. The same thing will happen with I2. And 2HI, since it's increasing by a factor of 2, we can say that if both H2 and I2 decrease by a factor of x, then it increases by a factor of 2x, which means that we now have 0.50 plus 2x. So now we can actually solve for x. So 0.50 plus 2x squared over 0.10 minus x squared. And that is equal to 50 as our equilibrium constant is. So, a little mathematical trick here, we can square root both sides to get this into a linear form. 0.50 plus 2x over 0.10 minus x is equal to root 50. Which, yes, I know, is equal to square root 25 times 2, which is equal to 5 root 2. Or you could just plug it into your calculator as square root 50, and you get 7.07. Okay? So, now we can solve for x. We multiply, we do the algebraic expression. By that I mean we just multiply by the denominator on both sides and solve, and well, do the distributive property, 0.50 plus 2x equals 0.707 minus 7.07x. So, now we combine the like terms, add 7.07x and subtract 0.50 from both sides. So now we have 9.07x is equal to 0.207. And so now we divide by 9.07 on both sides. And we get 0.023. Which, if we plug that back into our initial equation, okay, 0.1 minus that, square it, 0.50 plus 0.023 plus, times 2, and then divide that by, and square that, divide that by our answer squared. And we get what we get. So now I'm going to go off camera and actually check our answer, which is core to minimizing your rate of error. Okay? And after we plug in everything, uh, 0.50 plus 2 times 0.023 squared divided by 0.10 minus 0.023 squared. That gives us 50.28, which is actually very close to our original k value, which means that our x is a satisfactory value. So now, uh, not all of the rate constants are going to be are going to be like that middle of the road. Some are going to be incredibly large. For example, one of a very large rate constant is called Kf, or equilibrium of formation. So these are used for complexation reactions and stuff that goes very much towards the products. For example, silver plus ammonia turns into AgNH3 2 plus. And this is called beta 2, which is essentially just Kf1 times Kf2. Do mass balance, and this is actually going to be way, way, way greater than 1, something along the lines of like 10 to the 20th. So for these kinds of equations, we can say that our initial reactant is so small that it essentially goes to 0. Okay? Now, another example of the opposite spectrum. Something that is very small. Usually these are dissolutions of insoluble salts. So for example, AgCl, a very prominent example of an insoluble salt, Ag plus Cl minus. This is called KSP. And it actually has a K value somewhere along the lines of 10 to the negative 10th. So that means that the products, what's actually being formed, due to the K value being so small, they can essentially be treated as going to 0. Now, of course, the K value actually has value, so what you're actually going to do is take the square root of the K value and you get your individual concentrations, right? However, if you're combining this with another reaction, we can say that the concentration of Ag plus essentially is very close to 0. Okay? And so now we get to do one of my personal favorites, one of my personal favorite things to do in this unit, and that is combining equilibrium. So, if we go AgCl turns into Ag plus Cl minus, don't forget to use the equilibrium arrow. If you end up accidentally using the non-equilibrium arrow on the AP exam, College Board hates that. Ag plus 2NH3 turns into AgNH3 2 plus. Okay, so now, I don't have all the equilibrium values off the top of my head. So the College Board will actually give you equilibrium values that they want you to calculate. However, since I don't have these, I'm going to do a quick Google search. Okay, so after some preliminary searching, I find that the KSP for silver chloride is 1.8 times 10 to the negative 10th, and that the complexation of silver plus with ammonia has a K value of 1.7 times 10 to the 7th. So, what we can actually do, pretty neat trick actually, is we can add these reactions. Very similar to last unit when we did Hess's law. So, AgCl plus 2NH3 turns into AgNH3 2 plus Cl minus. So, what we can actually do now is we can, instead of adding these two equilibria together, we multiply them. So now our new k is equal to 1.7 times 10 to the 7th multiplied by 1.8 times 10 to the negative 8, and 10th, which is equal to, I have my calculator right here, 3.06 times 10 to the negative third. Adjusting for significant figures, we get 3.1 times 10 to the negative 3. Which, whilst yes, sounds like a pretty small number, remember that our original KSP was actually somewhere along the lines of 10 to the negative 10th. Which is an incredible improvement when you're actually trying to dissolve silver chloride. So now, we can move on to something that I personally love, called Le Chatelier's principle, except that I forgot that I need to actually teach you guys. So, again, if you add reactions, you multiply the K values. If you double the reaction, you square the K value, right? So, if you double the reaction, you square the K value. If you multiply the reaction by a factor of n, you raise the K value of that reaction by to the nth power. Okay? You add reactions, you multiply the K's together to get the new K. You subtract reactions, you divide the K's together. Okay? And again, that multiplying the reactions by some factor n is valid for all values of n that aren't, well, 0 or negative. So if you divide a reaction by 2, you square root the K value. Divided by 3, cube root it, and so on and so forth. Right? Now, we can move on to one of my personal favorites called Le Chatelier's principle. Le Chatelier's principle is an interesting principle, to say the least. So basically, it says that if you have a system, A plus B turns into C plus D. And let's mix it up. Let's have B be a gas and C be a gas. Right? Then, if you apply a certain stress, the equilibrium shifts to counteract said stress. So, for example, our K equation is equal to the pressure of C times the concentration of D divided by the pressure of B times the concentration of A. Now, the most direct way to stress a system is to actually increase the concentration of one of these, chemicals, for lack of a better term. So, if we increase the pressure of C, that makes it such that the Q value goes up, such that Q is greater than K, and the reaction shifts towards the left. If we increase the pressure of B, that means that Q goes down, and such that Q becomes less than K, and the reaction shifts to the right. A little less indirect is increasing or decreasing the pH, or the acidity. So, I'm assuming everyone has heard of the pH scale, but in case you haven't, here's a quick 30-second thing, right? The pH scale is basically measuring the acidity of a solution. As you go up the pH scale, I'm doing my best here, right? As you go up the scale, the acidity decreases from 0 to 14. You can have values less than 0 and more than 14, but generally they're considered super concentrated and highly dangerous to use. So, if we have a reaction, say calcium fluoride, if we have a reaction such as calcium fluoride, this fluoride actually is a kind of base actually. It will react with water, not fluoride, to produce hydrofluoric acid and hydroxide ions. So, if we decrease the pH, that means we decrease the amount of hydroxide, which shifts this equilibrium to the right. However, that also decreases the amount of fluoride, which decreases the amount of this fluoride, since it's the only source of fluoride, which shifts this equilibrium again to the right. Which basically you can have like a massive cascade just by like increasing or decreasing one variable. So now we can move on to a very specific application of this, the solubility product, or KSP. So now, I've already told you about KSP, sort of. Basically, if you have a salt AB, and it dissociates into a N plus, plus B, we'll say N minus, right? Then, the KSP is equal to AN plus times BN minus. Now there are certain like complications that gets into this. However, if you really want to write the general KSP equation, all you have to remember is the rules. You can never have a solid in the K equation, and you can also never have a liquid in the K equation. And again, C to the C times D to the D over A to the A times B to the B. Okay? So now we can move on to something called molar solubility, which is symbolized S. So say we have a solution of silver chloride here, right? That silver chloride dissociates into Ag plus and Cl minus. So if we actually do an ice table here, right? This is 0, this is 0. Since they're both 0 at the beginning, we can add x to both of them. And the KSP, as sourced earlier, is equal to 1.8 times 10 to the negative 10th. So what can actually do here is x squared equals 1.8 times 10 to the negative 10th. Which is a sort of weird coincidence, because x, if you recall, is equal to s, which means that s squared is equal to 1.8 times 10 to the negative 10th. Which means that in order to find s, we just need to square root it. Which we get 1.34 times 10 to the negative 5th. And now we go on to something called the common ion effect. Now, the common ion effect is really just a really freaking convoluted way of saying Le Chatelier's principle. Okay? Because what the common ion effect says is that if you have a common ion in solution, the least soluble salt will precipitate out because of the common ion effect. So, let's say that instead of dissolving it in pure water, we dissolve silver chloride in 0.1 molar sodium chloride solution. Ag plus is still 0, however Cl minus is 0.10 now. We again do plus x, x 0.1 plus x. And this is where we get into another trick that gets introduced into this unit called approximation. Now, obviously, I could do x times 0.1 plus x equals 1.8 times 10 to the negative 10th. And, of course, s equals x. However, this is actually super tedious because you're working with a really small number with a quadratic, which you can't really factor, so you have to use the quadratic formula. And on the AP test, you're crunched for time. So you don't really have time to use the quadratic formula. So now here's where we get into something called approximation. So we can say that point 1, since it's such a high concentration for this problem, we can say that point 1 minus x is approximately equal to point 1. So, which means that we get rid of this minus x term and say 0.1x is equal to 1.8 times 10 to the negative 10th. Again, s equals x, so 0.1s equals 1.8 times 10 to the negative 10th. So, now s equals 1.8 times 10 to the negative 11th. So now, after every single time you use approximation, you have to check what's called the 5% rule. Essentially, if your approximation is within 5% of the original concentration, then your approximation is good. If it's not, then you have to actually do the quadratic formula. In this case, we can see that point 1 is so much greater than 1.8 times 10 to the negative 11th that we don't even need to check the 5% rule. In some cases, however, if you're uncertain about whether you can use approximation anyway, and check with the 5% rule afterwards. Okay? It is now 12:40 at the time of ending this. I sincerely hope that you have a great time on your exam, and as always, good luck.